Good morning, ladies and gentlemen. Thank you for joining us for today's webinar entitled Managing Mineral Resource Risk, presented by Mr. Eric Ronald. The presentation will address common risks associated with mineral resources and provides recommended assurance and mitigation strategies to elevate, understand, and manage mineral resource risks. Mr. Eric Ronald is a geologist with more than 20 years' experience, specializing in resource geology, exploration and evaluation, estimation and geostatistics, production geology, auditing, and many, many other resources. I am now pleased to turn today's session over to our speaker. Eric, would you share your screen with us, please?
Hello, everyone. Good morning to you. This is Eric Ronald. Hopefully everyone is seeing my screen okay.
Looks terrific. Please proceed.
All right, I'll get rolling right into it. Thank you, Jackie. All right, so today we're going to be talking about managing mineral resource risk. So before we get into too much, let's get some definitions out of the way, as we likely have a variety of experiences in this audience. Let me start off kind of with a refresher of the basic definition. I think this is important as a base. So in this case, I've decided to use the CIM definition here. There are some slight differences between other reporting jurisdictions, such as JORC and the SEC, but they're all close enough for what we're really going to be discussing today. So you see I've got a few items italicized here. Really that phrase around reasonable prospects for eventual economic extraction is really important, as it implies a judgment by the qualified person in respect to the technical and the economic factors that are likely to influence basically the prospects of mining or extracting the mineral or metal. So that's a really important thing that we need to keep in mind throughout this whole process, is there is an economic aspect to mineral resources. So these economic assumptions, they typically include estimations around a cutoff grade, also geologic continuity at the selective cutoff grade, but it also brings into things such as metallurgical or process recovery, smelter payments, commodity price, product value, mining costs. The list goes on, even down to general and administrative costs, anything related to extraction. There are several ways of demonstrating this, really with the most common being use of a cutoff grade. But also this can be done in combination with, say, an economic pitch shell, stope optimization, or similar technique. Now, when we think of mineral resources, it's broken up into different categories based on confidence. So at the bottom bullet point, this is measured, indicated, inferred, highest to lowest level of relative confidence. Now, here's an example I like to use to kind of help explain some of those differences between that measured, indicated, inferred. And I like to use an analogy a lot of people are familiar with or maybe very passionate about. So let's go to fishing, right? Everybody loves this one. So inferred resource. So I've got the definition there, but this is around limited geologic evidence and sampling. So to have a resource, it might pass all these economic criteria. You know you've got something interesting in the ground that's potential, but really there's not a lot of data. It's a limited geological evidence and sampling. I like to make sure there's not a common there. It's not and or sampling, but it does include some level of sampling. So from a fishing analogy, you have thrown the line in and you're getting nibbles. You know there's fish out there, right? And this guy's got something on the hook. Don't know if you'll get it. Don't know if you won't. Not sure what it is. Could be an old boot, but there's some nibble out there. So next level of increased confidence, we go to indicated. All right, fish is on the line, right? So now we start talking around the definition of sufficient confidence to allow really the application of modifying factors. When I use modifying factors, that tends to be more the verbiage of reserve. But it's very important to realize that mineral resources and or mineral reserves are kind of just a continuum. So if you have enough evidence, sampling, sufficient confidence that you say, yes, we can now apply economic constraints, we can apply recovery constraints, whatever it may be, now you're in the world of indicated. Ultimately, it's the qualified person who makes that call, whether they feel you can make that distinction unindicated. So lastly, measured. Hey, fish is in the boat. We know we've got something. So this is confidence. We know there's fish here. We know they're biting. And heck, look, we got one in the boat. So really measured is that highest level of relative confidence for a mineral resource, really that you can now look at the quality, quantity, that is estimated with confidence, and that's key. There are some deposits out there that are even being mined today that never actually reach measured, believe it or not. There are inherent issues or uncertainties related to ore bodies that you just can't say. Like, we know we can mine it, but we're not still quite sure if what we predict is going to come out will come out. All right, so fishing analogies aside, let's move over into what is risk now associated with mineral resources. This is basically that uncertainty, or think of it as reduced confidence, associated with geology and deposit complexity, your fundamental data, so this would be typically drilling, physical, chemical data, and the estimation of all that information, estimation of the quality and the quantity of a resource. So additionally, risk is not all about doom and gloom, and it's not all downside, but it just represents unknowns. So often identified risks can also be opportunities with both positive and negative outcomes, such as you think an area is going to be low grade, turns out to be high grade. You get an area you didn't think there was much tons, turns out there's more tons. So it can swing both ways. The problem is that you don't know. It's hard to do planning if there's a wide spread of unknowns. So it's really important to realize the severity of that risk. It also changes based on the type of deposit that you have, right? And when I talk about risk, a lot of times it's in relative terms. So it depends on things like deposit complexity, also the mining method, cutoff grade, and other factors. So we're going to take a look at one of the examples with risk associated specifically with the cutoff grade. So looking at this graphic here, we can think of the x-axis down at the bottom as a degree of uncertainty around, say, a mean grade value. So it doesn't really matter what that grade value be. It could be gold, silver, copper, iron. It could be a variety of different things. If we piled up all the uncertainty together for a deposit, for say, we may see this being a fairly wide spread or narrow spread, depending on all these different factors of risk. The curve on here, I like to think the volume under the curve as can easily be conceptualized as the tonnage of our overall resource. All right, so now if we have a relatively low cutoff grade that we see in green, cutoff 1, we'll take a look at that one. In relation to the bulk of our tonnage and the spread of uncertainty that we have with relation to this grade variable, that associated risk is pretty low, right? Like the vast, vast majority of our volume is way above the cutoff grade. So if we're not quite sure about that cutoff grade, that risk obviously is pretty low. So now look at another scenario, different deposit, whatever it may be, cutoff grade 2 in red. Now, the resource risk is quite high, obviously, to the overall project success and valuation of the project if we get something wrong. If you can imagine that little red line swinging a centimeter to the left or right, that could affect large percentage volumes of your resource. Cutoff grade 1, move it a centimeter left or right, doesn't matter so much. Lastly, the same thing works, but in the opposite direction if we look at deleterious elements and thresholds for, say, ore and waste. There may be a critical element or mineral that is deleterious for a particular deposit, arsenic, fluorine, phosphorus, whatever it may be. But obviously, it's the opposite. If that threshold in which ore becomes waste is at the high end of your distribution, and that risk has a bit of a wiggle, well, the project risk is pretty low. So these are important things to understand. It's very, very difficult to actually quantify all this, but I think to conceptualize it is the key, and to understand where's your risk, where's your uncertainty in relation to your key cutoff grades. So I mentioned, cutoff grade, which is very, very key, but the deposit type, the relative complexity, and that geological continuity is many times just as important, if not more, as grade. So I really like this slide. It's a bit simplified, but I like it as it's a reminder that these all starts in resources with geology. Some deposits are just basically more simple and forgiving to those uncertainty. Others are inherently a bit more complex. Um, and then even if we dive down into particular commodities, we can appreciate the varying degrees of complexity that increase risk. All right, so we take a look at this, and obviously on the hard part of this, right, is where homogeneity is very low. The proportion of your actual economic minerals are very, very small. So in a case like this could be a kimberlite diamond. This could be in the alluvial side of things, alluvial diamonds, placer golds, or whatever. You never really know what you're going to get, right? Very, very difficult to understand, to sample, to get continuity, to estimate. If we go to the other side of the scale, we see things more stratigraphic bound, perhaps things a bit more continuous. Coal, the bulk commodities like some iron ores fall into this. Again, it's very generalized. Not all coal is easy. Not all iron ore is easy. Things of that nature. So you can imagine, like we take iron ore and we even break it down more. You can create a spectrum of that easy to difficult. Take a very consistent Lake Superior abandoned iron formation that goes on for kilometers and kilometers. Compare that to a magnetite skarn. Well, they both produce a magnetite concentrate. One is inherently really tricky, and one has a lot more leeway and can be a lot more forgiving. So why should we even care about this, right? Why should we manage mineral resource risk? Well, in short, mining can be a pretty risky game, right? So despite that inherent risk, mineral resources are what we have. This is the foundation of most of what we do here as a business. So resources are the foundation for reserves, which flow right into the mine plan and then go into the company business plan, not to mention the valuation of company assets as well. So really that only part of the deposit that we can't have an engineering or some innovative solution is the actual rocks themselves, is the ore body. So understanding that risk associated with the deposit's mineral resources, it allows for not only better engineering solutions, but ultimately a more realistic view of project value. And we see this over and over. These studies and these numbers are quite a bit out of date, but I think it's issues that we have seen in the past and we continue to see, where a CMMI study back in the late 90s was looking at a variety of projects and followed it through its study phases, through completion, operation, and so on. And 40% of these had problems with grade estimates. Hey, not a surprise. It's not an easy thing to do. And a quarter of them had issues with tonnage. And this is after they've gone through PEA, PFS, FS, so on and so forth. And in some cases, even mining for a while. If you're a shareholder, external stakeholders, community, whatnot, they really require better assurances on these reported technical information that supports resources. We see a wide variety out there in industry, but for project success, this is absolutely key. Once companies start producing, once you have an operating mine, especially multi-assets, really the valuation of the company, it starts to change a bit. It's not a junior explorer that is valued by the rocks that it has a right to mine or perceived gold in the ground or what it might be. Really that company becomes cash flow sensitive. It becomes focused on the short-term value, where that long-term value, really assessing the resources, and even you could throw exploration potential, is now treated as an expense. Oh, it's expensive to drill holes. It's expensive to put geos out on the rock and the outcrops. Well, we don't want to spend that. Let's reduce that, focus on the short-term value. So there's not only is the mining game a bit tricky, but there's obviously some inherent cultural issues and what the market demands, basically, that sometimes goes counterintuitive to what you hope to be able to do to reduce risk. So, in short, kind of the uncertainty and errors, they really do need to remain a major focus, and they are the main focus of a lot of economic failures that we see in the mining industry. So anything that happens, any kind of risk, any kind of uncertainty or unknown that's in mineral resources, this flows right through to reserves, right? So when we think about reserves, there's really only two inputs, right? It's pretty straightforward. It's all the stuff that makes up resources: land, sampling, interpretation, modeling, classification, all the geology, right? And then modifying factors. And that's an oversimplification, but this is all the study components. This is the engineering. This is taking stuff from the red oval and trying to understand it. How do we optimize mine planning? What does geotech make sense? The hydrogeology, metallurgical recovery process, so on and so forth. So all the modifying factors are standing on the resources and the understanding of study. You put those two together, there's your reserves. So if you can understand, manage, and reduce any risk in the mineral resource side, this feeds absolutely through not only to the modifying factors, but also straight into your reserves. Well, how well does your company understand this? So this is a key question that is a bit of a takeaway for this presentation, but it's an internalized, could be rhetorical, could not be. But it's important to ask these things as how well do you, either as an individual technical person or as a company, understand and manage your mineral resource risks? In my experience, the size of the company or the focus on a specific commodity doesn't necessarily matter. You can't always say all coal companies do it great and all gold companies do it better or something like that. It doesn't work like that. Good risk management varies greatly across the global mining industry. It really is more reflective of, say, company culture, technical understanding by the executive committee or the board of directors, but it can also vary. And some of the larger companies, you see large discrepancies internally from site to site, even if they've got multiple commodities, how they handle things. So hopefully your company doesn't fall into this sort of category where, we manage just fine, right? Nothing to see here. Just move along and there's a massive fire going on in the background. But these are things to ask, right? So we do see the kind of mid-tier miners, maybe small companies, even juniors, they tend to be relatively light on technical personnel, right? So there's not many people, there's not many hours, internal quality control, the checks and balances that are required to really have a proper risk management system. If you don't have the resources, it's hard to actually manage it correctly. Internal company standards for reviews and all, this is a really hard thing, and we'll get to this in a few slides, but to question internal company dogma and established methods, push a boulder uphill, right? It's absolutely near impossible to difficult. So there's some industry guidance out there, right? CIM is one of the better ones about it, and these are really good, but they have to default back to the expertise and the experience of the qualified person or competent person in JORC. So, not all QPs, CPs see things the same way, right? Like even within a company, same commodity, multiple QPs, they have different levels of subjectivity, different levels of risk tolerance, so on and so forth. So some sort of overarching company culture really starts to play into that. So across the industry, I'm finding more and more there's a general ignorance of technical details and risk by management teams. A lot of times the management teams are very focused on some particular aspects. That's why they're in management. They are looking at, say, production, controlling costs or whatnot. But they then rely on technical personnel to manage and understand the resource risk. And a lot of times technical folks have difficulty communicating that at the right levels, and management communication just falls down. So consequences. Yep, this happens a fair bit. This is unfortunate, but as a short example, this is a North American gold project that it's had significant changes to the reported mineral resources from one year to the next. This is not about depletion or anything like that. This is about fundamental changes to the deposit interpretations, and not having a real sound understanding of their structural complexity early on in the project, which means as new data comes in, you get big swings in resources. So from one year to the next. The consequences in this case, it's really about erosion of confidence in the company's capability and understanding by shareholders and stakeholders. Why would an investor or an investing trust look at trusting this company to see, if their material changes every time they update their model? They go, what are these guys doing there, right? And there's issues with the ore body itself because of the complexity around it, but there's issues with not spending the amount of resources to really to understand it. So cases like this, they get really messy, they get really quick. Shareholders are obviously upset, the company goes on the defensive, and we see things turning pretty ugly. So now let's get into the meat of mineral resource risk. So, here's a graphic that I like to use to explain the components that make up mineral resources. Pretty simple thing. I like to use the analogy of, say, a house or building. All right, we've got to start with a solid foundation and build up from there. So in the case of mineral resources, this is absolutely the fundamental data. So this is the drilling data, chemical observation data, physical data that support the entire process. So let's start looking at all the associated risks with the data. One of my favorite sayings, garbage in, garbage out. Absolutely. If you can't trust your initial data, what's the point? Everything's built on it, right? And so all the assumptions and interpretations based on that are based on faulty assumptions. Nothing holds up. So there is error associated with all input data. Now, whether that's analytical, geological interpretations, logging, physical, this could be metallurgical or density, geotechnical work. There's always issues with that. Sample collection and the preparation errors. Now, these are typically much greater than analytical. Like labs are great. They know their business. When they get their kilogram of sample or 30 grams of sample in the door, they do a good job. But how that kilogram showed up, the variety of drilling, the variety of sampling collection techniques, so on. Usually the error is magnitudes larger in the actual collection of that sample as opposed to once it hits that analytical lab. The sample spacing is absolutely key. So you go out and you drill your ore body out, right? 100 meters, right? That seems like a nice round number. Let's start there. And oftentimes that is then picked out of the air and never gets refined. Once you understand, wow, this is a really complex ore body. Maybe we should shorten this up. Well, that's expensive. We can't do that. Well, 100 worked fine in the past. Let's keep using 100, or whatever it might be. I find there's very few studies that actually go to understanding what your ore body geometry and that intrinsic variability, basically Mother Nature not cooperating, and how it relates to how much data you have at an appropriate spacing. So you can say, I got a hole here, my next hole, yeah, no idea. They may not even be connected. So where your data is in space, how it's collected, and then the management of it. Oftentimes I see this stuff falling to the least experienced person, or it's just contracted out to somebody else. In cases where you don't have the resources, absolutely makes sense, right? And yeah, least experienced person out on the drill rig, that's fair, but who's checking, who's peer reviewing, who's supervising, who's training? If all of your information and resources is based on that foundation and you have someone who doesn't really know what they're doing, bit of a risk, right? And then a big pet peeve of mine, biases, interpretations, and sampling. They increase the errors even more. So when somebody goes through and starts selecting out particular samples, this will be a good one to test. That one, not so much. Instantly, everything is already biased. And I'll touch on this one here a little bit more. So I mentioned some of the sampling issues. There's huge amounts of error that go to sampling. And these are some pictures. I'll run through these here pretty quick. But I think we've all seen these sort of things at exploration sites, mine sites, or whatnot. There's a lot of ways to collect samples. And the best thing to realize is none of them are perfect, right? There's always error, but you want to try to minimize the error the best you can. So over the course of a deposit and a mine, this could all be from one site, right? And a myriad of sampling techniques. Should you treat them all the same? So yeah, upper left, this guy here is taking, looks like a portable Pima or XRF and shooting a blast cone, right? Like no idea what he's shooting. This stuff has anywhere from a square centimeter to a wider range of what it's actually looking at. Obviously he's looking at what's just on the surface, what layer did that come from, how homogenized, et cetera, et cetera. The middle one, yeah, I love this one just because I have no idea what the heck's even going on here. Somebody's trying to put a boulder through a rifle splitter and just question after question. We take a look at the upper right. So, this is where we see mineral segregation in an inappropriate drill rig where it's drilling it out, but what wants to be recovered, which is all the white stuff, the good stuff, that's just blowing in the air, right? And that's a softer mineral, and that kind of gets spread all over the place. So any sample that you grab from the cone underneath is instantly biased because the good stuff's blown all over the place. And anybody who's done blast hole sampling knows that digging a cone is probably the best you can do, but it's not great, right? And there's issues between samplers and everything else. So you can start to get an idea. Relative sample error can be absolutely huge. So when we start looking at all this fundamental data risk, you go, oh my God, there's so much, like it's just a big mess, right? Well, what are some ways that we can try to manage this, right? And a lot of this is have a system for consistency and correct sampling based on your operation, material sampled, and so forth. Make sure staff are trained. Like nothing's going to be perfect, but consistency can be key, and make sure that there's a process in place. The location of samples are critical, especially in drilling. If there's uncertainty in the collar or downhole locations, all the interpretations in the model are going to be off, right? Because the deeper the hole, the more deviation there probably is, and Lord knows where this thing actually goes. So when you select a downhole survey method, just make sure that it's appropriate for the rock types, whether you're using a magnetometer or gyro, if you've got magnetic material, whatever it may be, and that those intervals for your downhole survey, they're not too great, right? It makes sense for the deviation you're seeing. Audits and reviews, right? This is a great way to try to understand the risk management. Bring in some outside experts. Have a look at improving your process. Is there a better way to do it? What's your neighbors doing, right? It's like another set of eyes. This can be an annual thing, one-off costs, but it can really make a huge improvement to the overall process. Now, this is what I was saying on pet peeve a bit earlier, is don't let your samplers make decisions on what is or what is not sampled. Too often I've seen logging or sampling geologists make a call and they go, this looks like ore, and this looks like waste. Now the term ore should never even be in the vocabulary of a geologist, right? So ore suggests it's material that's passed a series of economic and technical thresholds. But that changes over time, right? Economics change, project economics change, market costs change, pricing changes. So the data needs to speak for themselves. Let the rocks tell the story. Don't let the logger make the biased call. Obviously, robust QA/QC. This is an important aspect where you need to have the feedback chain that goes back through. It's not about just saying, yep, we've got a good QA/QC program where we've identified errors, we've done retesting. It's about the feedback loop. The point is to identify those issues and then correct them, not just say, yeah, we entered one sample, QC sample per 20. Like, okay, well, what'd you do about it, right? So having a variety of data is also an important way of managing risk. Like this seems a little odd, but these all relate to the same ore body. So by having multidisciplinary data, geophysical, surface downhole, so on and so forth, structural data, chemical data, metallurgical data. All of this aids in the big picture understanding of a deposit, and you start to see correlations. You start to see how these relate to each other. And if you can start to see that, now you can start to identify issues before they might happen. And so it's important to understand and look at this stuff holistically. Lastly, whether it's a geologist, data manager, administrator, geostatistician, or somebody really needs to be regularly looking at the data, calculating statistical analyses on the raw data, understand behavior, trends, characteristics. Sometimes the best way to assess and manage risk is actually just look at the data. And it's shocking to see a lot of cases that there are companies out there that just don't do that. So it can be a long process to mitigate this fundamental data risks, but it has to be properly resourced with the right people and given adequate time and budget to do it. It's not impossible, but there are some things to keep in mind. So now we're going to move over to the first pillar of mineral resources. This is the interpretation and domaining of geology. So here, as opposed to analytical data, now we're getting into the world of subjectivity and interpretation. Obviously, risks around there. So interpretation risk. This pillar is just, it can be fraught with errors and it can be fraught with genius. It's an absolutely difficult one. But this needs to be refined and change as projects develop. In some cases, especially projects with limited data, the geological interpretations and the volumes of material that are being modeled can be the largest source of risk and uncertainty to a project. This is where a good deposit model and interpretations of structure, lithology, mineralization, alteration, and the overall geology of a project is key. And it's best to pull this together as early in the project as possible. Obviously, there's cost constraints, But the more complex ore bodies, veins, highly structural controlled deposits, minor changes in that interpreted geology can really materialize to massive increases or decreases in that volume of mineralization. Now, especially in exploration projects, I often see grade shells used as the defining volume for mineralized material, where there's little or no knowledge of the controlling factors. You work with what you got, right? But this can easily result in like unrealistic volumes, blobs of overstated volumes, especially when you get modeling staff who get thrown on software and maybe they don't really know what they're doing, and it becomes a challenge to say the least. The inverse can actually happen in mining operations, where maybe you have the mine geologists can get overly conservative in their mineralized volumes, where they take to modeling as it's a worst case scenario type model, realizing that essentially they're going to get their bonus for positive reconciliation, right? So if the volume's a little smaller and it always comes out a little more tons, well, they're the hero. Both have issues, both have biases. It's good to understand that. So how do you manage this interpretation risk, right? So these are some challenges. There's some very readily available tools that can kind of semi-quantitatively assess the risk in mineralized volumes. This would include generating multiple interpretations by different geologists or getting a few geologists together, using probability tools and softwares like Leapfrog. And really the most straightforward one is just having a model peer reviewed at sufficient detail, not, hey, I need this by tomorrow, but really to dive into it by somebody who's got experience with that ore body or that type of mineralization. As you'd imagine in data poor zones, not much drilling, the variability and the risk increases, while where you have more data, more drilling, it's really constrained. That interpretation can be a lot more constrained and thus reducing that volumetric risk. So we look at the images on here, using Leapfrog probability indicators based on a couple drill holes. You can see how someone would interpret this one way versus another. And if you modify these probabilities just a little bit, what it can do to the volumes here. And the same, the other one's image on the right, just looking at different grade shells, with the pink being more constrained and that kind of purple shell being around it being another interpretation that's still honoring the data, but significant volume differences. Next, we move over to tonnage. So this pillar's probably the most unloved or really overlooked. It's a determination of a tonnage factor or simple bulk density. So when we look at total metal from a value of your project, simple equation, right? Volume, that interpreted geologic volume, times the density, times the grade, right? But okay, you spend all this time working on the grade, maybe you spend a lot of time determining the geology, and then what happens to density? Well, it's 1/3 of the factor there, right? And you don't want that to be the critical factor. So oftentimes I see great efforts and cost applied to improve the quality of geology models, chemical data. And then if you're doing a due diligence or an audit, well, what density do you guys use? And then I hear things like, wow, it's the average for granite or limestone or whatever it might be, or we got a few data and we just average across the whole deposit. It's just like, whoa, this is one of the most key inputs to determine tonnage and thus your total metal value of the deposit, but it doesn't necessarily get the attention that it deserves. Thus, the errors associated with testing, with sampling, they're rarely considered or quantified. If you've got multiple or complex lithology, variety of alteration, mineralization, density can vary greatly. And how you test it, right? So if you've got clay, void, or competent rock, what about friable material? You immerse in a SG apparatus and clays turn to mush and they go away. Well, you're not getting something good out of that. And is it taking into account things like sample size, scale? So you're looking at bulk samples, you're looking at core, you're just looking at chips, grab samples even. So even those small changes in density across a very large volume of large deposits can drastically change that. So what are some risk management techniques here? Number one, it's key to have geometallurgical and metallurgical inputs to characterize the deposit. Oftentimes the Mets, they've collected a whole variety of data to domain the deposit in various zones of similar metallurgical characteristics, of course, but typically that includes density, right? Met might be your best source of density. So number two, operational data. It can be key, assuming you've got an operation, to feed back into the density determination. So operational teams like the drill and blast crew, mine planners, especially geotechs, they'll have operational databases related to density data that they collect on a variety of things. That should be incorporated. Number three, be sure to collect enough density across the deposit. Just a few, quote, representative samples, that's rarely sufficient. And what's considered representative is a bit of a headache, right? So make sure you collect enough to be statistically significant samples across all these different lithologies, domains, mineralization, whatever. And don't forget about the waste. That's very important. So number four, as a mining operation progresses, you got to make sure this is continuously updated. It's not just assume a 2.7 specific gravity. It was assigned back in the feasibility study 25 years ago. Well, it might not be the same. You've drilled a lot more. You've expanded. Everything you knew back then has changed. Number five, always be skeptical. I just say beware, buyer beware. When densities are calculated using some type of derived value, say based on mineralogy or rock type. Not saying they're wrong, be skeptical and challenge it. I find these regressions tend to only hold true in really large data sets and should always be backed up and supported by lab data. Plus, most have a long list of assumptions that were put in the day they started, and obviously those assumptions they commonly get forgotten after a few years. Like, oh, well, this only applies in certain parts of the pit, and this only applies for this, because it doesn't take into account pyrite or other densities, whatever it might be. Let's move over to estimation. So estimation risk, there are volumes of books, and I'm not going to get into that obviously here on concerned with inappropriate or appropriate estimation means of grade deposit. Yes, estimation can represent a significant risk and uncertainty in many mining projects. Often I see estimation completed in one extreme or the other with an overly simplified strategy, say using a small number of samples, inverse distance squared, or they swing the opposite, where you have a geostatistician come in and there's a field day with complex nonlinear techniques that may or may not actually be necessary or appropriate. So common issues that I see with estimation risk are really around inexperienced staff performing the estimation, not really understanding what's happening. The search ellipsoid going in the wrong direction because software companies can't be consistent, right? Extrapolation of data way beyond where you've actually got drilling and sampling, and there's a long list of things, and including smoothing, right? There's folks out there, schools of thoughts where you go, okay, well, your neighborhood must be optimized, which can, in some cases, result in a very, very smooth estimate. That will end up getting basically a distribution of block grades across the whole deposit, average almost resulting in the mean. And that's not what you want either, right? So how do you manage this, right? Estimation risk management. It can be as simple as just getting the right people, right? Right person in the right chair to oversee or to review some of these estimates. This can be an annual thing or every other year, but it's also key to make sure that the estimation and the results make geologic sense. Recall that the house analogy that I've been using. Well, that foundation of fundamental data is key here, especially in this pillar, as the resource is only as good as the data that goes into it, and it can drastically affect the estimation as biases can potentially influence a significant volumes of resources. Estimation validations is important along with peer review. It's important sometimes to trial different types of techniques, methodologies, make sure these things are together. Try to determine what is the best one. And if you're lucky enough to have reconciliation data, it should be used absolutely all the time. Lastly, there's some well-established tools such as simulation that can aid in quantifying the risk through probability. This is really, really useful in uncertainty and risk assessment. I've seen, I wish this would be used more often. I've seen it pretty limited, but it's a whole topic in and of itself, and I wouldn't do it justice here, to say the least. Let's move over to our last pillar. This is classification. Really, this is assignment of risk, somewhat subjective risk assessment used by qualified persons to communicate relative risks, right? All right, so the risks that we see in classification, it comes down to a few issues. really because it's at the discretion of the qualified person. Oftentimes we see significant differences in approach of how you classify it. Ultimately, it's up to the company to determine who is that competent and qualified person to perform that role. And as a shareholder or stakeholder, always be wary of projects when the QP gets replaced halfway through. It's very easy for companies to potentially over-influence the QP. When classification becomes a bit of an afterthought, oftentimes you see things being oversimplified. Classification based on, say, just one factor, say like just distance to the nearest sample. And this ends up with our spotted dog, as a beautiful picture there shows. So, these are where you've got individual drill holes that result in like concentric cylinders in 3D, if you want to think about it like that, decreasing classification as you go away from data. Now, this is just, it's wrong. It doesn't align with CIM definition standards. Obviously, it can be a step, but never should be final. And an important question to ask when classifying a mineral deposit is, does the classification, measured, indicated, inferred, and not classified for that matter, truly correlate to mineral resource risk? It needs to take into the accounts of what you understand of overall risk. And it also should be viewed overall, like a global for the whole deposit, but also how does it affect local? Now, mineral resources, by definition, it's focused on the global perspective of the entire deposit, but it's also important to consider the local scale. These are important things. Lastly, because it is subjective, it is, as I mentioned before, it is potential to have the QP subject to outside influences, the ulterior motives of classification. So this is always a bit of a tricky one, and one of the things that does not make being a QP a simple thing is there may be particular management targets. We need a grade, we need a tonnage. They feel a share price bump or whatever it might be that's heavily influenced how the classification. We really need measured. Well, the data will tell you whether you have measured or not the executive team. So what are some items to help manage the classification risk? It's typically to take a step back, look holistically, look long term. Don't be allowed to be influenced or bullied by company expectations or needs. It should always be a combination of multiple factors. I pinched that image off of like a GIS, but it's a good way to think about it. It needs to take into account data quality, geologic understanding, density, estimation quality, all those pillars, right? All the pillars, the foundation, everything we've been talking about. Also, distance to data, variogram plays a big role in this as well, the quality of the estimate. All these need to be incorporated into how you decide what's measured, indicated, inferred. So some in the industry also argue for, say, production reconciliation to be the true measure of confidence. And I do like this a lot. The problem is that it's a very difficult thing to do, where you try to have a classification based on, say, quarterly annual grade tonnage within a percentage of prediction, right? Problem is this only really works in large, consistent ore bodies with a long history of quality reconciliation, a long history of production. And if you're an early stage producer, or even if you're just an explorer, it doesn't really work. So our last bit of this house analogy, this building analogy, is the documentation, kind of that final capstone on the process. Brings it all together, right? Got to have this thing documented. So just like a whole house, it doesn't quite work unless there's a good roof over it. So with documentation, if it's not documented, it didn't happen, right? And that's kind of an auditor line, but this is important. You need to have that updated, clear, thorough documentation to really provide proof and process of what actually happened. You can't improve something if you don't actually understand what the process is. It's important it gets regularly updated, and it shouldn't be something that's like, well, we wrote that book, but what actually happens is this, right? It's just, yeah, what do you do? It's got to go in there. And it shouldn't be a cookbook. Click here, click there. It's really, why are you doing this? What goes into it, right? So there you have our nice little house, strong foundation, solid pillars, sturdy roof, all that good stuff. But then, the wrecking ball, right? We love this one. So management, auditors come in. Are they going to knock this thing down or not, right? So one overarching big picture of this whole thing is you can't properly manage mineral resource risk without that corporate risk management. We've easily demonstrated the business importance of understanding risk to mineral resources here. But does that risk get the appropriate level of attention, time, budget from the management as it should? Some companies are great at this, while others treat mineral resources as something that's the problem, say, the site geologist has to deal with. That's not their concern. So who's ultimately accountable at your company for mineral resource risk? Is it the site geologist or the CEO? Does that executive committee understand the resource risk? Is it a focus of the executive committee or the board for that matter? Does it become an annual burden on site personnel for reporting? How ingrained is that understanding mineral resource risk to the business across the whole process? So the system process risk management, this is really a key aspect. Unfortunately, this can't be done by technical staff alone. This isn't a, run some stats and fix it sort of thing. This is an overall company process. It really needs to be led from a top-down bit. This needs to be management endorsed. The paper trail, who did it, who those responsibility individuals are, the QP, the people working under the supervision of the QP. It's got to be reviewed. The system process risk, it's got to be looked at peer, internal, and external to make this whole system right? This is the glue that kind of brings it all together. So how do you know it's holding together, right? Check the system. This is where audits and reviews come into the mix. First, you need the system, right? Then second, after you have the system, you need to test the system. A perfect way to test it is through a detailed auditing program. This can assess those known unknowns, the stuff you don't know, and then also those tricky unknown unknowns, or what the heck do we not actually know that we haven't got to yet at that part of the ore body? What are going to be the problems that we're going to have next year or 5 years from now? So usually the best bit from an auditing and review is a combination of internal and external audits that really will result in the best results. Now, both are challenging. I got a few things on there that show they are challenging, but you get the system in place, you got to test the system. So taking a look at conclusions here, really, we all know mining mineral resources. I said before, it is a risky business, but it can be a risky business, right? If we allow it to, if we don't spend the time and the budget to really try to sort out our issues at the beginning. It's really critical for mineral resource risk to be understood for overall project success, right? Like we said before, that there are a lot of projects that fail because of shortfalls within assessment of mineral resources. There are lots of different areas where risks come in across data, geology, tunnel classification, the foundation, the pillars of all that. So you're getting little bits of risks, you're getting a little bit of cracks, you're getting a little bit of mold, you're getting a little bit of, whatever kind of house analogy you want to use in each of those. You pull them all together, and that's where your increased chances of failure come. So you can see relatively small expenditures to really unlock that significant value. Or reveal there's a potential for a large value destruction, right? Is a lot of times being proactive costs a lot less than being reactive. So a process of internal assurances, the external audits, these really provide a lot of value to identify those risks before you have catastrophic loss of value. And there has to be, absolutely must be, management support. Champion at the executive committee or board of directors level for success. Somebody who's ultimately accountable and responsible. So if nothing else, I want you to take away a few key takeaways here. Resources are fraught with errors, and risks need to be understood, assessed, and addressed. And remember, the deposit, the geology, the rocks, it's the only part of the mining operation that you can't come up with a really bright, good engineering solution for. Risk reduction is cheap compared to the alternative, right? And that's the reactive side. But it does require management systems, support, and resources. Resources being, in this case, people, time, money. If you don't have all three of those, it's not going to succeed. You got to check the system with audits, and it's best to take an overall holistic view by geologists, engineers, as well as management to improve that. So my last slide here, before we go to questions, is an absolute shameless plug. If you like this topic, if you're passionate about or like to know more, you know, and you're in North America for that matter, my colleagues and I, we're going to be presenting a one-day short course going into a lot more detail, getting into some depths and specifics on managing mineral resource at the upcoming AEMA conference that's set for late November, early December. At this point, we hope that it's on. We hope everyone's well and healthy, and it happens in Western Nevada. So some details there if you want to check it out. So that's it for me. Thank you very much for listening. I very much appreciate it and happy to take some questions.
Thank you, Eric, for an excellent presentation. I'd like to open up the question and answer period to our attendees. Please use the chat panel and I'll read the questions to our speaker. Eric, the first question also comes with a comment. Why doesn't typical resource reporting outline the range of possible outcomes in a given cutoff grade? Sensitivity analyses typically only varies the cutoff grade. The implication of present reporting standards is that there is no uncertainty in the resource estimate at a given cutoff grade. Again, the question is, why doesn't typical resource reporting outline the range of possible outcomes at a given cutoff grade?
I love this question, and there is so much discussion, maybe arguments, dare I say, yelling perhaps, within the industry around this, because I wholeheartedly believe in the intelligence of the average investor who could digest and understand grade ranges and uncertainty, whether it's probability or just a high-low sort of thing, when it comes to disclosure of mineral resources. What regulators and the powers that be have said is that it is too confusing. And what will happen is if you show a a grade range, highs versus lows based on, say, a P90, P10, something like that, is that by default, engineers, economists, valuators, assessors, et cetera, will always take the worst case scenario, realizing that he said risk is a two-way street. There is opportunity for good and opportunity for terrible bad in some cases. So because of that human nature to always take the worst case scenario, you'll see overall projects undervalued. If someone takes the initiative to put out a range, they are almost doing themselves harm compared to another company or another deposit that may have similar tons and grade, who just says, here's our mean, here's our one number, average grade, and here's the tons. And if you say, well, probably between here and here, again, all the valuations will say lowest grade scenario. So there's not an easy solution. I wish there was a great answer. There's a lot of discussion and comment within industry about that. I would love to see something more than a grade tons curve. And I think some of it is onto the QP to try to at least talk more about risk, talk more about quantitative risk assessments or other ways of putting it. But ultimately, your final statement, your table one, your this is what our grades and tons are, will typically just be a single number, at least for the short term in the future. So hopefully that addressed that question a bit.
Thank you. The next question, what is your view on estimates of inferred resources at a specific deposit that are based on sampling analogy deposits in the region, but not the specific deposit related to the resource estimate?
Yes, neurology, exploration through neurology, or being in the right zip code, right? If I park my RV in Beverly Hills 90210, I am in that zip code. I have a place to sleep, but I'm probably not a Beverly Hills real estate agent. So, it's one of those that desperate times calls for desperate measures. If you do not have the data, if you do not understand your ore body well, people will try to find the next best alternative. Now, if you're making inferences on your ore body based on the world-class high-grade Olympic Dam deposit that's sitting next door, you're probably stretching things a bit. I guess I don't have a problem with it as long as it's disclosed, as long as it's clear that you're making an absolute wild guess and it's probably not true. But it's something that's better than nothing, and it just needs to be clear on where that's coming from. It inferred is really risky by nature and by definition. But again, I think it's down to the disclosure. If you state what's going into it, then the informed investor or audience reader can make their own decision. That's a good question.
Thank you. The next question, what is the best method for determining bulk density? How often is testing throughout exploration drilling?
So the best method will depend on your rock type. Unfortunately, I wish I could just say it's, ASTM da 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 or something like that. There was a slide back in there on what kind of rocks you have. If you've got clay content, if you've got voids, if you've got friability, if you have vugs, if you have any sort of these characteristics that could bias the way density or specific gravity is tested, it needs to be investigated. So there's a lot of different ways of testing specific gravity or density. Investigate what your options are. If you don't know, do a couple different ways and see what those differences are. Try to understand that. When it comes to density testing, with a lot of other data as well, more can be better, but also the spatial representativity across the deposit. If you know your rock type's changing, well, you need density from both rock types. If your alteration is changing, you need density data from all of those types. I find a combination of a lot of data helps, even downhole data. It's sometimes doing gamma density logging in relation to laboratory testing can provide a whole lot of data for relatively cheap. As I mentioned before, during production especially, you get density all over the place. And some of it can be used, some of it is rubbish, but determine what makes sense and try to pull it all together and ask yourself the basic question is, does this make geologic sense for your density testing? So sorry, there's not like a silver bullet that'll solve all the issues here, but investigate it, understand it, and relate it back to your rocks.
Excuse me, thank you. The next question. In your opinion, what are the main criteria for using geostatistical methods for estimation?
Ooh, the criteria for using it. If you've got an ore body, use it. How's that? I think there is always a case to use geostatistics in any kind of geology, exploration, mining. Now remember, geostatistics is just the application of the spatial component, space, the geoside, to evaluating data from a statistical method, right? There are complex methods using simulation and nonlinear. The maths can be quite complicated in some cases, but as part of understanding your geology, your geologic continuity, and the spatial distribution of grade or whatever metal mineral you're looking for, geostats falls absolutely into that category. Always needs to be investigated. Usually the limiting factors are data. If you don't have enough, you're not going to be able to make any sort of valuable interpretations. Just like regular stats, you try to do a histogram on three pieces of data, it doesn't tell you anything. But if you've got 30 or 300 or 300,000, now you can make some better inferences and interpretations on it. So I would say as a criteria would be number one, have a deposit. Number two, have data. And number three, make sure you have enough data that it can be meaningful. But it always should be looked at. It's an important part of the process.
Great, thank you. Our next attendee has a comment. He says, a very good presentation. And his question is, how to reduce the CP discretionarity on the resource estimation?
This is a challenge, absolute challenge. There's an interesting study that was done recently through the Colorado School of Mines that was just surveying a variety of different qualified persons in North America, I think specifically looking at NI 43-101, and getting an idea of, well, how do you classify? How do you estimate? What is good? What is bad? And as you can imagine, the returns or the results of that were all over the board. No two QPs are the same, just like no two human beings are the same. Everyone has their own inherent risk tolerance or appetite for risk or whatever it may be. My recommendations and thoughts on that subject is peer reviews, documentation, and consistency in the guidance that's out there. So things like CIM provide guidance. There are groups out there that put out best management or probably better termed good management practices of these different aspects of estimation, data collection, whatever it may be. If QPs can fall into a broad category of following those, then you're at least in the right ballpark, right? And there will always be differences, but if you can make those differences smaller, if that makes any sense, um, then that's a good place to start. But I mentioned peer reviews. So getting multiple experienced people to review stuff. And this can be through external auditors, internal auditors, whatever. And it can be another set of eyes, the gut check, does this make any sense, or the sniff check on the thing. You will find people will less likely go to the extremes and more fall into kind of a middle mainstream if there's someone else reviewing, auditing, or being accountable for how they're doing classifications, how they're doing their estimate, whatever it may be. Sorry, it's a long answer to that. I think there's a few things the industry can do better, but just ensuring companies do reach out for audits, do reach out for other sets of eyes. It'll give them the assurances that yeah, their QP is not on an end member, they're not an extreme, they're not an outlier. That's a good question.
Thank you. I'd like to remind our attendees that this webinar is being recorded. It will be posted on the SME website and made available for you to download and view again at your convenience. It also will be posted in the SME store for people to purchase if they did not have the ability to do it today. We have time for one more question. Eric, how to make the estimation more depending on data and less on the CP only?
Mm. Um, I'm not sure if this is going down like the data-driven models with things like machine learning and artificial intelligence, which is a whole another hour-long conversation right there. Um, what we have at the end of the day is our data, what the data says, our interpretations of the data, and then our subjective, I guess you call it also interpretation and classification that goes into it. Um, Information has to be data supported, but ultimately the guidelines for all the reporting jurisdictions rely on the experience and the expertise of the QPs to make a call. And this is a tough question. You would hope that all estimations and the data analyses and even like geologic models and interpretation, they're all database. They're all based on drilling and mapping and assaying and so on and so forth. Um, I guess from a classification point of view, and where the QP really makes a big difference in there, is to make sure that when you're doing classification, that you are using a variety of inputs and not just everything on the west is measured, everything in the east is inferred. Well, why, right? Is use a combination of actual analytical data, and this can be estimation quality data, things like kriging efficiency, distance to nearest samples, or mean distance to samples, a variety of inputs that then become part of the overall classification. There will always be subjectivity into it, but the more you can have, I guess, data justification that goes into it, the more you could see consistency. If you know that the estimation quality is good in one particular area, data is always sound, you trust the geologic model, there's enough information, at least in that area, multiple QPs should at least agree, yeah, that's going to be pretty good. Now the conversations between measured and indicated, that's a pretty good conversation to have. When you don't have a lot of information and now it's just subjectivity, that's where things get a bit complicated. So yeah, not an easy question to answer, but maybe I touched on it at least. So hopefully that was helpful.
Thank you, Eric, for sharing your expertise with us. It was a fantastic presentation. We're getting lots of notes saying very good job and thank you. Would you have any final comments for our attendees?
No, just thank you for listening. My apologies if I spoke very fast. You can listen again on half speed or something. But there's a lot to cover, obviously. There's a lot that goes into mineral resources, and there's a lot of areas that risk gets introduced. If you're a QP, if you're a manager of mineral resource or an executive committee or board of directors member, start to understand these things. Start to ask questions about your site, your company, your deposit. How do you handle density? What goes into your estimate? Who's making the calls of this? What help do they have? What did the last audit findings? Start asking questions and you'll start finding out things. Once you understand the state of things, now you can start addressing or mitigating those issues. So anyway, thank you very much for your time, for listening, and all the excellent questions.
Thank you very much, Eric, and thank you everyone for joining us. On behalf of SME, please take care, stay safe, and this ends today's session.